Okay, it's 2 o'clock, at least on my computer. So welcome back, everybody. Welcome to the first afternoon session of today. And it's my pleasure to announce the talk of Professor Hans Feichtinger, with whom I've also a personal relationship as one of my professors in Vienna and a postdoc employer. And so he will talk about invariant function spaces as double modules illustrated via Fourier standard spaces. Please, Hans.
Thank you very much. So essentially, I will come to some relatively old topics. So the main references are about 35 years old, but there was very much renewed interest in this topic due to work of the group in Novi Sad, Stepan Filipovic, Bojan Brankovic, and so on. We have a joint paper in preparation or so. And this is about function spaces which are more or less function spaces on abelian groups. And Hans Reiter once said at the time when I was a PhD student and my friend was working on the Heisenberg group, Feichtinger, you are the abelian one and he is the non-abelian one. Now I'm ending up talking about non-abelian actions on abelian groups. So I don't know, it's up to you to decide which direction it is. I will of course have to tell you what Fourier standard spaces are, but essentially this is a huge family of spaces which are covering many other spaces, but you can think at the very first of LP, FLP, or other spaces that you have in mind. So the main so I want to mention that these, more or less all these things that we can do can be done for Banach spaces of ultra distributions on locally compact abelian groups. This would be rather abstract, and let's say the ultra distribution setting is more convenient or interesting for the people in Novi Sad. I will stay with the kind of simple special case of Euclidean spaces, and because everybody is familiar with tempered distributions, I will more or less talk about Banach spaces of tempered distributions. So this is in the spirit of Ernst Triebel and his theory of function spaces or so. What I will discuss is more or less a topic which is related to the question, how many spaces can you have with the same norm? So we all know if you start with L infinity, you can have inside L infinity the bounded uniformly continuous functions, the functions vanishing at infinity or so. So essentially the question is, how can you do in a systematic way more spaces? Very often, people are restricting themselves to the closure of the test functions, so the Schwartz space in the given function spaces. So you would restrict your attention to C0. But then you have the problem that you would like to reach all of L infinity, and then you have to take some kind of weak convergence. And all that can be put in a rather systematic framework using the theory of Banach modules, which I will tell you. So not to frighten you, but to give you an idea about a certain diagram which was developed at that time, I will show you one big diagram which will be explained in great detail and will be specialized or so. And that's kind of, if you take a completely abstract point of view, then you can make out of one space, theoretically 10 spaces, in practice 6 spaces for reflexive spaces, just one space or so. But you can discuss how the diagram looks for a given space, and I think this gives you a lot of information about the different spaces. I don't go into the direction of the non-commutativity, but one could reformulate part of these things with the Schrödinger representation of the reduced Heisenberg group. But I will take the naive point of view of convolution and pointwise multiplication. So essentially, I started this when I was discussing compactness in function spaces. And then you have the classical Kolmogorov theorem saying, well, a bounded and closed subspace in LP of RD is compact if and only if it's equicontinuous and tight, which means shift is equally continuous for all the functions in your compact set. And all the concentration is not just an individual property of functions, but it's a joint approximation. Now, I was getting quite early familiar with the theory of Banach modules. And in the theory of Banach modules, you would say, okay, LP spaces are L1 convolution modules who can operate by convolution with L1 on an LP space like L2. But you can also do pointwise multiplication. For example, you take the Banach algebra C0 of continuous bounded functions vanishing at infinity, and then you have a bounded action of C0 on LP. Having tightness means you multiply all the function with one given plateau function with compact support, and the error is uniformly small. Equicontinuities means you are smoothing all the functions with one very compressed Gauss function, and the approximation quality is equal. So you have two Banach modules, one with pointwise multiplication, one with convolution, and they are not commuting, but not so badly far away. So that's the topic of this talk. So what is the abstract viewpoint? I would say a Banach module is just a pair, more or less, of a Banach space combined with a specific algebra of operators. That's actually what we are doing quite often in harmonic analysis. We are not just interested in all the linear operators from one space to another, but those which are commuting with some Banach algebra action. So, of course, every Banach algebra itself is a Banach module over itself because you can multiply internally from left to right. But if it's external, and again, L1 convolved with LP is a typical situation, then you have a Banach module. So the most important property, aside from bilinearity and the ingredients, it's really like a multiplication, is the associative law. So the left-hand side says, if I apply the action of A prime on an element B first, I get another element in the Banach module, and then you apply another element, but you could do equally multiplication internal to the algebra, and then apply the resulting algebra element on the B. So that's what we do all the time when we're using star for the convolution or pointwise multiplication. We even don't care because there is no distinction between internal convolution in L1 with L2. We just say it's associativity of convolution. But that's most of the time really what the case is. Now, there is an important term that you use. Well, I should say I'm mostly interested in Banach algebras which do not have a unit, but which have bounded approximate units. So that's the realistic situation when you're doing harmonic analysis. L1 is definitely not having an identity. The Dirac measure is the only candidate, but it doesn't belong to L1. C0 cannot have the identity because constant 1 is the identity. It does not vanish at infinity or so. So if you do not have an identity, you would like to have still that you can have a lot of products and that the action is not trivial. I mean, everybody can define a trivial action. Every element A bullet B is 0. That's not interesting. So we are interested in first in essential Banach modules, which are those where the linear span of A bullet B coincides with all of B. Now, if you recall the Cohen-Hewitt factorization theorem, then you can say that if you have an essential module and a Banach algebra with bounded approximate units, then this set actually is all of B. So it's not clear a priori why A bullet B is a linear space. The sum of two products should not automatic or cannot be seen automatically as a product, but that's part of the truth of the Cohen-Hewitt factorization theorem. Okay, so what are the two prototypical examples? I have mentioned them already. C0, functions vanishing at infinity with the sup norm. I don't care here that I have a C star algebra, and L1 with convolution. Now, as we would like to have a situation which is symmetric with respect to Fourier transform, it may be interesting to not to use C0, but the Fourier algebra. It's an interesting maybe observation to say that if you look at the Banach space, let's say LP, and you have it is an essential module over C0, it's also an essential module over FL1 or vice versa. This is just because FL1 also has bounded approximate unit. It also has a dense set of compactly supported functions. So if the Banach algebras are very close, it's really not exactly important what you choose. So you could, for example, take CK, the functions which have K derivatives bounded, and so in C0, for example, that would be all possible. Now, just to recall, what is a bounded approximate unit? It's an indexed family with a discrete or continuous parameter, so formally it's a net, and I will write alpha to 0, alpha to infinity or so, kind of saying that it's better and better if these products in the algebra or in the action as a module act in the appropriate way. I have already mentioned that LP is a good example, but if you look at the Banach space L infinity, then the product equals, and it's the same as the closed linear span of L1 with L infinity, to the uniformly bounded continuous functions. It's quite easy to find out that the essential part of L infinity with respect to the module action is just the uniformly bounded continuous functions. And yeah, maybe I'm leaving out the rest of this discussion. Now, I will use these symbols A and G in the upper and lower position. So what we have seen so far is we have a pointwise algebra, and B sub A is the essential part with respect to the pointwise algebra action, or by the coinuit, I said already, it's just A times B. What is it in practice? It's the elements which have good decay. If you take L infinity, it's the functions which are bounded. They can be step functions, but they are decaying at infinity. If you take LP with P less than infinity, it's just all of LP. You can look at the essential part of the essential part. That's always just the essential part. So think of this as a procedure like taking the interior of a nice set. Now, if you look at the L1 situation, I will restrict myself to the unweighted case. I try to avoid Berling algebras in this talk. Then you have this well-known convolution inequality, which is a result of the continuous and isometric translation operator in the LP spaces for P less than infinity. Now, how can we make something complementary to the essential part? So how can we enlarge it? And for this, I need the notion of a Banach module homomorphism. So if you have two Banach modules with action number 1 and 2, you can say, well, I have a Banach module which a linear mapping, a bounded linear mapping between the normed spaces, which respects the module action. So either I have action number 1 before I apply the operator, or action number 2. So most of the time you will say, I mean, you can take the convolution theorem. Here you have convolution, Fourier transform, put it into pointwise multiplication. Or you just have associative law. A multiplication operator is commuting with multiplication. A convolution operator with whatever is commuting with convolutions. And actually, these are the translation invariant operators in the engineering. So this is kind of what we have. Very easy prototypical example. If you take the operators commuting with C0 multiplication, well, these are just the multiplier on C0 into C0, you get the largest space of all bounded continuous functions. And of course, the sup norm on the right-hand side is the same as the operator norm of the multiplication operator. A similar situation is Wendel's theorem for L1. You're asking what are all the operators from L1 into L1 commuting with translation. And you verify it's the same as commuting with L1 convolution, and you find out these are all the convolution operators by bounded measures. Bounded measures contain L1 as a closed subspace, and that's what we need. So I define B upper A to be the module homomorphisms from my algebra into the space itself. And then we have a nice set of rules which just say it's like the closure. The closure of the closure is the closure. The closure has an interior, which is the interior. So the last occurrence of a letter just tells you where you end up. But now we have two such operations, and these two operations do not commute. I am not allowed to say that convolving first with G and then multiplying is the same as first multiplying this. But if you go to the infinitesimal generators, these are translation and modulation, then you can say, well, they commute up to phase factors, and that's not so terribly bad. So there is some hope that with these two module actions and using hull and kernel, I mean essential part, you might get some exchange rules. So just taking two lower cases or two upper cases, or then the mixed cases, you easily write these symbols, but you can continue. So observation number one, once you make the new space smaller or bigger, it preserves, it has the same structure. So you can repeat, and of course it's now interesting to change the order. That's why I'm writing B sub A super G, and actually, sorry, I'm writing G instead of L1 of G. So I'm taking all the operators from the essential part of in the A action. Then I take all the operators from that space, from L1 into that space. So that's a super G. Then I ask, well, what are all the elements which are approximated by compactly support, and so on. This is kind of like an alphabet or so. And now the observation is, and I'm trying to collect the main observation in one slide. If you make any long chain, actually you just can reduce it to a chain with two letters, one A and one G, and it's the last occurrence which counts. So the list of spaces that we have here is already more or less exhaustive for the long symbols. The next observation is that these two guys, the lower lower and upper upper, are the same. And actually the lower lower is the closure of the test functions. And the upper upper is what is called the relative completion, the weak star limits of bounded sequences from the original space. Now, if you go back, and I have to jump, I had in the original thing labels. So there's a +1 here and a -1 here and a +2 here and so on. And this simply means if you tell me you have observed maybe that in your case, all the elements which are approximated by compactly supported elements are just elements of your space, and this is this space, then I would say -3 is a collapse. But then you will have a collapse at +3. So in this diagram, you have inclusions from lowest space to biggest space, they're in this family, and you have coincidences, and I have no general rule between 5 and 6, maybe somebody can find something, I don't think it is, but there is a coincidence in one part of the figure if and only if it's another part. I'm going now to, if the space is minimal, you have a collapse at the lower level. If it's a dual space or if it's maximal, sometimes people use the Fatou property to prove such things, then you have it at the top position. So what are Fourier standard spaces? Well, I have different versions of it, but for this talk, I choose this one. These are just Banach spaces in the spirit of Treble, containing Schwartz space and sitting inside in a continuous way the temper distributions, but where L1 is acting by convolution and FL1 is acting by pointwise multiplication. Typically, you get it by saying, well, time frequency shifts are isometric, and the Schwartz space stands in the space. From translation isometry, you get convolution action. From modulation, you get FL1 action pointwise. If you want, you can increase it, map the Schrödinger representation of the reduced Heisenberg group. I skip this part or so. And you have a lot of things. Now, the interesting thing is that in this family, there is a smallest guy, really smallest Banach space with all these properties, and that's the space that I introduced as S0 because it was a Siegel algebra and zero reminding of minimality property. In the book of Charlie Gröchenik, you find it as the modulation space M1, and the dual space is just S0 prime. have many, many different characterizations, but roughly speaking, this dual space is the space, I call it the space of mild distributions, the space of all tempered distributions with a bounded short-time Fourier transform. I'm not going into the details here, but now a very important slide is this one. If you start with any space, maybe you start with LP, because LP spaces are considered important, also a little bit difficult for Fourier analysis. You can take the Fourier transform, but you can take also the dual space. So you can take, for example, FL1, and you can say, well, I like to do Fourier functional analysis. So either you say this is FL infinity in the sense of tempered distribution, or you call it, this is the space of pseudo measures. So something appearing in the theory of pseudo differential operators, of course. You take two such spaces, you take the intersection. If you take a weighted L2 space that's not exactly in this setting, intersected with a Fourier version, you would get a Schubin class, for example. That would be a deviation from this strict regime here. For those who know amalgam spaces, you can take amalgam spaces. The Fourier image of an amalgam space of the form WFLPLQ would be modulation spaces. All these spaces are part of this family, but I find it most interesting that you can take, for example, Fourier multipliers. The space of Fourier multipliers is the space which may pointwise multiplying FLP into FLP. And then you can go back and you can ask, well, what are the convolution operators from LP to LP? All these spaces have all these properties, and you can make a diagram and you can ask what is the situation of the diagram. I personally think that's an interesting question also to apply the metaplectic group to such spaces. So to ask very similar questions for fractional for images of LP under the fractional Fourier transform. This seems to become also quite fashionable nowadays. Now, in this family, there are the minimal Fourier standard spaces and the maximal spaces. If you start with a minimal space, the dual space is again a space of tempered distributions, and it is a maximal space. On the other hand, the converse is true. If you give me a maximal space, I can show you how to get the pre-dual, so it's the dual space of a space obtained in the following way. Take your space. Take the closure of the test function in this space. Take the dual and then take the closure of the test functions. Just as an exercise. You know that L infinity is a dual space. So what is the pre-dual? Well, I have to take B0 first, which is the closure of the Schwarz space in L infinity, which is C0. The star now means I have to take the dual of C0, which is the space of bounded measures. Then I say, now please take the closure of the Schwarz space in the bounded measures, which is just L1. Yes, L1 is the pre-dual of L infinity. And there are many similar situations where people are using nowadays, I don't know, Morey spaces and other spaces where I think exactly this situation is coming up. Now, for reflexive spaces, so P between 1 and infinity or FLP, everything is reducing in a dramatic way. Both B and B prime are minimal, and it's equivalent. So if you have a Banach space, which is minimal, I mean a Fourier standard space, if it's minimal, the dual space is also of the same type. It might not be minimal, like L1 is minimal, dual L infinity is not minimal. But if you look at this, and if it turns out to be minimal, then it must be reflexive, and the formula above gives you a good diagram. So just to tell you, without big explanations, how is the situation for the minimal spaces, so maybe L1, I mean, not L1 is not good, maybe. Here you have more spaces down here, and the diagram says you may have non-collapsing at level 1, 2, and 5, and 6 independently or together. If you have a dual space, the accumulation of spaces with this difference is in the upper level, and so the potential non-collapsing properties are at 3, 4, and again 5, 6, which I don't want to discuss here. If you ask how many spaces can you actually get, the infinity norm is a good example. Now, depending whether you start with a minimal space or with a maximal space, you get always 6 spaces. It's the same 6 spaces, but the labels are different. You can imagine if I go back here in the case of L infinity, I have coincidence at level 1, 2. For C0, starting from this, I would have coincidence at level 3 and 4, but I get the same different 6 spaces. I don't want to give you the details, but just mention it. You have C0 as the small guy, L infinity as the big, the dual guy. You have the uniformly bounded continuous functions. You have the functions which are L infinity and decay at infinity, but don't have to be continuous. Or you have the functions which are not going to infinity, but if you convolve them, they are going to infinity. So maybe step functions with higher and higher oscillations, and if you smooth it, each time you smooth it, you get an C0 function. So you really get 6 different spaces. And another interesting case is L1 and M-bounded functions. So it's really L1 is the elements which are continuous shift, test closure of the test functions, and M infinity has all these other properties. So the remarkable property as opposed to LP space or L infinity is the bounded measures can be approximated here, the last term, also by compactly supported bounded measures. So I was writing down some case how this is. Yeah, so I forgot to finish this slide. So if you take the L1 case, you can say, well, we're talking now about the convolution operators on L1. L1 to L1, this is L1, and all of the convolution operators are infinity. If you talk about L infinity, we know these are all the pointwise multipliers of L2. So Fourier multipliers of L2 is just L infinity. So we can say, okay, translate this result into the Fourier domain, then you have just the Fourier algebra and the Fourier-Stiltes algebra. They're just 2 elements for the diagram of the Fourier multipliers for p equal 1, and we have 6 different spaces for the Fourier multipliers for p equals 2. So I think it's an interesting question, what happens for p between 1 and 2. I'm quite optimistic, but I have no complete proof yet, that it should consist of 4 different spaces. So it's known, for example, that not every Fourier multiplier on LP with p larger than 1 can be approximated by compactly supported ones. Or so, but this is kind of the situation. And you can go for many more spaces and ask the same question. And I think that's quite interesting and tells you a little bit about the structure of the spaces. Now, I would like to end with some, continue with some characterizations which are not in that paper of '83 with Waldemar Braun. And it's a way to characterize these various symbols using only approximate units. So maybe I mention here E alpha stands for Dirac sequences and H beta for plateau functions. So these are the approximate units for convolution, and these are the approximate units for pointwise multiplication. And maybe I jump first to the concrete situation. You might think of compressing a Gauss function or a rectangular function, then you have a Dirac sequence which acts nicely as a convolution identity. And in this setting, the support is shrinking, so our parameter is a continuous parameter, rho goes to 0. If we do the same thing and go to the Fourier domain, of course, L1, a normalized compression goes into dilation. So what we have here is actually the situation that we have with summability. We all know the Fourier transform of an L1 function may not be integrable. What are we doing? We're choosing a nice function h, like the Gauss function. We're multiplying it, but we would like to have the effect minimal, so we would like to have it very flat. I personally prefer very much for this kind of illustration the trapezoidal function. So you take a trapezoidal function from -1 to +1, supported -2 to +2, and you stretch it more and more. So you're capturing more and more, but you're cutting off, you're localizing. Now, the good thing is for the slides, for these characterizations before, you can choose any approximate unit here, any bounded L1 approximate unit here. If it's true for one, it's true for any other, and the same here for pointwise multiplication. So again, think of here, there's a smoothing operator and there's a localization operator. And now The first thing is, how can I characterize the closure of the test functions? Well, these are the functions which can be approximated by regularized versions of these things. I'm saying you're giving me an LP function. It's not, maybe not local enough, so I localize it and then I smooth. Or I smooth first and I then do a localization. And here you have all these, there should be 5, but there was not enough space, characterization. You could say, well, it's in the closure of the test function if and only for every good enough Dirac kernel, every large enough plateau function, this is good. So alpha, beta is a pair of indices. If both of them are good, you're fine. That, of course, implies that you can take a limit in one order or in the other order. And actually, you can also choose the order of multiplying first and then convolving. Whatever you're doing is you're always characterizing the same space. So this is maybe a good exercise. I found this a little bit more tricky. I'm showing you the slide. These mixed guys, especially number 2 to 5 in this second slide or so. There's a fine distinction between quantifiers that either you are saying, I'm saying for every individual beta, you have a good relation with respect to alpha. For example, here you would say, if you give me a bounded continuous functions and you localize it, you get a compactly function or compactly supported continuous function. Of course, this is a function which is equicontinuous, therefore approximate units are working fine. So the space of bounded continuous function appears at this level or so. On the other hand, you might say, no, I'm smoothing a function, but I'm watching at this only a cutting off, and I would like to know whether the tails are harmless with after convolution. So here you would have functions which after convolution, you are having good decay. Maybe the function itself in the pointwise sense does not decay so well or so. So these spaces, these quantifiers, one has to get used to it, but you clearly see there's a change in the order of the operations, but also in the order of limit, and whether you're saying first you fix the interior and then you take the limit in the outside or the opposite order. So in this way you have these diagrams. Okay, I think I'm coming more or less to an end of my presentation already, because this is the old paper where this diagram was showing up. It was formulated in the setting of what I called standard spaces. So in a way, it took me some time to show to the people in Novi Sad that it really covers also the spaces of ultra distributions, but it's in a very abstract language. But it's also true for Banach spaces over locally compact groups where the algebra might be different than just the Fourier algebra. So this was just for illustration purpose. Okay, in the paper of Dymowski, no, this paper, the third one, I found more or less exactly the tempered version of this, where instead of L1 and FL1, you have Berling algebras, but with polynomial weights. So we have the isometric situation, which I was discussing here with L1, FL1. The tempered situation is described in this space. Those two papers are the ultra distribution or the abstract situation. And all this, from my point of view, arose from discussions about compactness in Banach spaces of functions, which also was done quite a while ago. And I think I should stop here and thank you. With some hint on where you can get other talks and at our NOHAC server. Thank you very much.
Thank you very much, Hans, for this interesting talk. Are there any questions? So maybe I would like to ask a question. So you told us about, so can you disclose a little bit about what types of function spaces you're now studying or interested in this project with the people from Novi Sad, and I don't know if Jason.
Okay, yeah, well,
involved.
with Novi Sad, they have a recent paper. I think actually it's more or less this paper. No, that one, yeah. They were saying if you take all the functions all the tempered distributions or ultra distributions which have a short-term Fourier transform in a space of this type over phase space. So they were saying we could take a tensor product of two spaces, you're getting a function space on the phase space. And then you're taking all the functions with the short-term Fourier transform in such a space. Now, my argument viewing from modulation space theory is, oh no, that's dangerous because these spaces are not solid. So they don't have this Banach lattice property, smaller functions might not be, but it turned out that's completely irrelevant or so. And then we had a discussion and I said, well, but maybe I can identify some of the spaces that arise in this way. So you're giving me, for example, LP with LP1 with LP2 or LP with LP tensor product in the sense of projective or let's say injective tensor product. And then you're saying, I'm taking all the temporal distributions having a short-term Fourier transform in that space. Can you say anything about it? They were able first to say it's proper subspace of L1, but it turned out some of them are just, again, amalgam spaces with explicitly, exactly of the form local FLP and global L1. So you can see how behavior on the short-term Fourier transform in one or the other direction is influencing the resulting inverse Fourier transform. So I think it's the study of the inverse short-term Fourier transform, so a kind of back projection operator on tensor products, and I think that by itself is an interesting property.
May I ask a question following that?
Yes,
does that depend on how does that depend on the window then?
Pardon?
How does that depend on the type of window that you're using?
These characterizations are more or less all independent of the window. As usual, if you take a window in M1 or a 0, then you get always the same space.
Okay.
That's.
Thank you.
Yeah, but it's a natural question. Yeah.
I have one.
I would also like to ask you something about generality. So for RD, it is impossible to see, if you don't make a distinction by notation, who is the group and who is a group,
right,
because they coincide. So it was invisible in a very natural way. Now I get that if you have an abelian locally compact group, so if it is abelian, you could repeat most of what you showed us.
Yes, I mean the point is if it's discrete, the smoothness issue is disappearing somehow, and if it's compact, the decay properties. So it should be non-compact and non-discrete, which of course doesn't mean that it has to be self-dual or so, but that's why the Euclidean space is kind of not so exceptional for that kind of discussion.
Okay, I agree. So to make it interesting, it needs to be.
But let's say periodic numbers would be absolutely. You just take it as it is, and all the things have nothing to do with. I mean that I'm doing the approximate units by dilation. It's kind of for convenience of presentation only. Yeah.
Sure, but actually my question was about the non-commutative case in which the dual object is no longer of the same type of the group itself. Is it still possible, because you still have some good Fourier theory if the group is not very, very bad, if it is type 1, let's say. Is it still possible to put these formulas to work?
Yeah, I would say, well, let's say if you take LP of a non-commutative, non-compact group or so, I would still say you still have ordinary pointwise multiplication with C0. So you can describe concentration on compact sets, and you have equicontinuity. You may have to distinguish between left and right, of course, but it's more or less the situation that you have for compactness criteria also. So part of the paper is completely, maybe I'm too much influenced now in the presentation by the desire to do it in the spirit of time frequency analysis, where the symmetry between time and frequency is kind of an issue. But the original paper was more in the spirit of general locally compact groups. Yeah.
Okay, so the theory would be somehow not very well balanced because of the difference between the initial object and the dual.
Yeah, it's kind of the argument that I'm just having time shift, frequency shifts would not be reasonable. I would really have just two independent operations, but I have pointwise multiplication and I have convolution on any group, of course. And these are the two things which really matter and which are used in the proof. So I'm not using any Fourier theory in that old paper.
Oh, okay, thank you very much.
Yeah, I think we are done.
Are there any other questions? I think somebody, I don't know.
I
Somebody
have
started. Ah, yeah, the one. It was you.
it's maybe a good opportunity for me to sort of Feichtinger about. I know, yes, modulation spaces are very recognized between this family, but I want to ask you personally, yes, which was your motivation to introduce these spaces in mathematics?
Yeah, okay, it's in 2 sentences. I wanted to do something like Biasov spaces or smoothness spaces on locally compact abelian groups. Okay, exactly the discussion that we had. And since there is not always a dilation available, dyadic intervals have to be discarded. I mean, you can take powers of a generating set in sigma compact groups, and somehow I realized that these BUPUs, these bounded uniform partitions of unity, are a good way to deal. And even Hans Triebel was recommending this to do. He said, well, you're losing all this theory of maximal functions. Time theory doesn't work anymore. But it turned out to be a kind of a different story. And now from the point of view of Corbett theory, we realize it's just different groups acting on different Hilbert spaces or so. So if you take, I mean, for the community here, I think Corbett theory would be a good starting point to understand. It's just changing from AX plus B group wavelet theory Biasov spaces to the Heisenberg group and do that kind of thing. So but it was a kind of a naive way, and amalgam spaces were needed to do modulation spaces as amalgam space on the Fourier transform side. Because nowadays that's also a little bit mixed up. People say, yeah, okay, whatever. But if you send me a short reference, there are 2-3 papers where I'm summarizing it, or even informal notes where summarizing this. I think it's interesting. But I think we should stop here.
Okay. Thank you very much, Hans. Many thanks. And yeah, so I'm. Should I stop your screen sharing? So it's my pleasure to announce the second speaker.